Hello, I'm Brian. I'm here to talk about our paper, Steering No-Regret Learners to a Desired Equilibrium, which is joint work with a bunch of authors, Gabriele, who's in the audience, Ioannis, who is not, Federico, who's not, Stephen McAleer, Andy Haupt, who's also in the audience, Nicola, Gatti, Vincent, Conitzer, and Tuomas, Sandholm, who's also in the audience. Okay, cool. So the setup for our problem is kind of very simple to understand in some sense. We have an arbitrary multiplayer game, which I'll denote by gamma. And each player I has some finite strategy set and some utility function, which we assume to be linear in that player's strategy. And the game is going to be played repeatedly. So on each round T, each player is going to output a strategy, which is just some point in this set. And each player is going to get some utility that is a function of every player's of all the players' joint strategy. And the behavioral assumption that we're going to make on the players is that the players have no regret, no external regret. So the players are trying to minimize this their external regret, which is simply the difference between the utility that they actually got and the utility that they could have gotten by playing some fixed strategy in hindsight. And we're going to assume that the player's regret is going to scale sublinearly with the time horizon. So something like t to the 1/2, where by this O gamma here, I'm going to hide polynomial factors depending on the gain gamma. Okay, so it's pretty well known that in this sort of domain, no regret algorithms, if you just let them run, kind of fail spectacularly to reach desirable equilibria, or even any equilibrium at all. No regret algorithms are known, for example, not to converge to Nash equilibria, much less any good Nash equilibrium. So in this picture here, we have a simple game, which I'll go into more detail later, but suffice to say, it's a extensive form version of a stag hunt or something like this, where there are two equilibria in this diagram. They're at the bottom left and the top right, and the bottom left equilibrium is this hare equilibrium, which is kind of welfare dominated by the stag equilibrium at the top right. Okay. So as you can see, if I start the learning at some various starting points, for most of these starting points, the learning dynamics will converge toward this bad equilibrium at the bottom left. So kind of we don't want this. So what our setup is going to be is we are going to take the role of a mediator. And this mediator is going to be allowed to observe the players playing the game. And on every round, the mediator is going to be allowed to pay the players. So at the beginning of the round, the mediator publicly selects some payment function, which is some function that maps the player's joint strategy into some number, and the mediator will select one such payment function for each player. And then when the players select their strategies, the mediator is going to pay the players according to the strategy that they play. And basically, you can think of these payments as just being added on to the player's utility function. And the overarching question that I'm going to discuss in this talk is basically, what can we do with such a mediator? When can we use this mediator to steer players toward better outcomes? So the main insight is essentially no regret algorithms can be steered. The main insight is positive, is that no regret algorithms can be steered toward much better outcomes without paying too much in some sense. And I'll clarify exactly what I mean by too much, because some of you are probably already thinking the trivial thing, which is, if I allow this payment to be arbitrarily large, I can steer the players to do whatever I want by just giving them money, right? So the interesting question is, how little money can I get away with using? So we can see here that in this example, which again I'll elaborate on later, with payments that decay as the time horizon grows, I can steer the players toward that top right equilibrium, and this will be a more general phenomenon. So in general, our goal is going to be, given a pure Nash equilibrium X star, I'll devise a strategy for the mediator such that the players, under only this assumption of that they are no regret learners, are guaranteed to converge to this desired equilibrium. So essentially, over time, the difference between their average strategy and this target strategy decays. Right? And you might say, okay, well, pure Nash is a little bit restrictive. I'm going to relax that. But for now, it's a pure Nash. Okay. So the problem, as I sort of hinted at, the problem that as I've stated it right now, is kind of trivial. Because what can I do? I can pay the players a lot of money to play the right strategy, and then they will be steered toward the right equilibrium. Great. Okay, but that's not exactly very interesting. So okay, now the question is, can we do this without paying too much? And what do I mean by too much? I will want my budget, the total amount of payment I give to all the players, to scale sublinearly with the time horizon. So I want my budget to scale as little as t. Okay, and you might note here that this budget is the actual budget that I pay. Right, this is the actual amount of money that I have paid to the players, rather than the amount of money that I offered to the players. I could have offered much more money over time. Question.
So you're giving utility equal to what they would have gotten UIXT already, plus the payment?
Yes.
I'm wondering, is that payment allowed to depend on other players' actions at time step T?
Yes. Yes, the payment is allowed to depend on the joint strategy XT.
So another clarifying question, as the mediator, do you know what the good Nash equilibrium is in
Yes.
the game?
Yes.
Because in some cases, even figuring out characterizing the equilibrium is challenging.
Oh, absolutely. So for now, I'm assuming I'm given the game and I'm given a pure Nash equilibrium of that game. That is part of the inputs for now. I will relax the assumption of pure Nash later. I'm not going to relax the assumption of being given the equilibrium because computing equilibrium is hard. So for the sake of this talk, an equilibrium is given. Okay. So again, we have this steering problem, which is I have a pure Nash equilibrium, and I want to steer pairs to it. The first result, which is rather simple to show, is that if my budget is not allowed to scale, if I have an absolute constant budget, then essentially I can't do that much. And I'm not going to give a full proof of this, but I'm going to give some intuition. And the intuition is essentially the players can basically steal all of my budget and then go back to doing what they want. It turns out that no regret on its own is not that strong of an assumption, and players can do very wild things while still being no regret. So players can in particular do this. They're just going to take all my money and then go back to playing a bad equilibrium. So essentially, as the mediator, I must constantly offer at least some slight incentive for the players to maintain the equilibrium as they're playing. And this already forces my budget to grow with the time horizon. Okay. So first, I'm going to discuss steering in normal form games. And steering in normal form games turns out to be a consequence of the literature on K-implementation, if you're familiar with this. There is a well-known result of Mulder and Tenhelt from 2004 that says essentially, if I have a pure Nash equilibrium, then there exists this function pi, this payment function pi star, with the property that if I add this function to every player's utility, then the equilibrium becomes weakly dominant. And it also has the property that at equilibrium, I pay nothing. So how do I construct this function? I'm going to use the payment function that essentially does this. If my equilibrium here is at the top left, I'm going to pay the players a lot of money if the players play the equilibrium and another player doesn't play the equilibrium. So essentially, I'm playing players to catch each other in deviations. So, okay, now I'm almost done. There's a little bit of a problem in that weakly dominant is not quite enough for us, because no regret learners are not necessarily forced to play weakly dominant strategies. So on top of this, I'm just going to add a very small payment for the players in equilibrium to force the players to actually go there. And this alpha is going to decay, is going to grow sublinearly with t. So our first result is that in normal form games, I can set alpha to be something that decayed with t, and the steering is possible with both the gap and the budget growing sublinearly with t at t to the 3/4. And this p here, as a reminder, this p here is the bound on the payment per iteration. So this was my payment function is a map from the player strategies to the range 0p. Okay, so this is essentially all there is for normal form games. For extensive form games, the story becomes a little bit more difficult. If the original game is extensive form, I'm going to say it doesn't really make much sense for the mediator to observe the player's full strategies. Because the players are just playing the game, right? The full strategy encodes the player's complete contingent plan on about what they would have done if another player would have done something else. But if I'm just watching players play an extensive form game, I'm not going to observe this, right? I'm only going to observe the path of play. Okay. So for example, if I reach this node here, at this node, the mediator should not be allowed to know what player 2 would have done, right? Because the game is over. The game is over and player 2 has not acted. The mediator should not be allowed to know this. Okay, So for extensive form, we're going to formulate what we call the trajectory feedback setting, which is very simple to state. Instead of selecting a payment function that depends on the player's strategies, I'm going to insist that the mediator select a function mapping terminal nodes, Z. Z is the set of terminal nodes, mapping terminal nodes to the range 0p. Okay. And the actual payment given to the players is just going to be the expected payment. So X is going to be some mixed strategy profile of the players, and the players are just going to get their expected payment. Right? And the question is, under this model, is steering still possible? The first question you might ask is, okay, well, for normal form games, we saw that steering was possible by K implementation. So can we still do K implementation? Can we make this desired equilibrium at the bottom right dominant? Well, how do we make this dominant? Right. In order to make this strategy dominant, I would have to add a payment there. But any payment that I add there would necessarily appear in equilibrium, right? Because this node happens with positive probability in equilibrium because player 2 is playing stag. So in order to make this strategy dominant, the budget would have to grow linearly. Which means essentially that the strategy that we've come up with so far of using implementation doesn't work. We cannot steer by implementation in dominant strategies. And in fact, we can formalize this. We can actually state something stronger by essentially generalizing the stag hunt type of example, which I won't get into here, but suffice to say you can generalize this and you can say that in extensive form games, steering with a per iteration budget that is absolute constant is impossible. So if this per iteration budget P is constant, I can't do anything. So in some sense, I have to have this per iteration budget growing. Okay, so how do I steer in this example? In this example game? Well, the solution turns out to be to add a payment here. What does this payment do? Well, at first, player 1 might be playing hare most of the time. And then since player 1 is playing hare, player 2 is going to also learn to play hare initially. But the thing that I've done by adding this payment here is I've made stag dominant for player 1. So player 1 will eventually learn to play stag. And once player 1 is learning to play stag with enough probability, then player 2 will say, okay, stag has the best response to stag, so I'm going to play stag 2. And it turns out that this phenomenon, so what am I doing here? I'm essentially doing sort of the same thing that I'm doing in normal form games, which is to say, I'm saying that I'm going to reward player 1 for catching player 2 doing something that is not the equilibrium that I wanted them to do. I'm going to reward player 1 if player 1 has played stag, that is the equilibrium, and player 2 has played something that's off the equilibrium. And that phenomenon, so although the weakly dominant strategy implementation doesn't work anymore, the phenomenon of paying players to catch each other in deviations still works. Paying players to catch each other in deviations is still going to be the intuition here. So more generally, to steer in extensive form games, what I'm going to do is I'm going to pay the players a large amount of money for playing equilibrium actions when at least one other player has deviated. And I'm going to pay everybody a very small amount of money, alpha, if everybody plays the equilibrium. And this payment alpha has the same intuition as before. It's basically to keep the players around the equilibrium, to turn something that's quote unquote weakly dominant into something that's strictly dominant. Although again, the dominance intuition fails here. And our main result here is that with appropriate settings of hyperparameters, we can, and we should note here that the payment is also growing with T now. With appropriate settings of hyperparameters, we can get both gap and the budget, the total gap in the budget while scaling sublinearly in T, which is again the thing that we were seeking. Okay, now a couple slides ago, I said that we were going to discuss relaxing this assumption of pure Nash equilibrium. I'm now going to do that. So how do we steer when we have Nash equilibria? Well, we are going to convert every problem into a problem for about pure Nash equilibria. So if I have a mixed equilibrium, what I'm going to do is I'm going to consider the game with advice, where the mediator not only gives payments to the players, but also essentially takes the role of randomization from the players. So the mediator is going to suggest actions to the players, much like in a correlated equilibrium. And then the mediator is going to tell the players not only that not only what the payment function is, but also, you know, as the game goes, what their actions should be. Okay, and by doing this, in this augmented game where you know these mediator actions action recommendations are explicitly encoded in the game, there is a pure Nash equilibrium, which is obey the recommendations. Right, so now I've converted this problem into a bigger extensive form game where I've reduced to the previous situation where I have a given pure Nash equilibrium. The pure Nash equilibrium is now just obey all the recommendations. And you might ask, you might ask the question: is this even necessary? Do I have to have advice? And it turns out, as you see on the slide, the answer is yes. Steering to mixed equilibria is generally not possible, even in normal form games. So basically, the intuition for this is that in a game with both pure and fully mixed equilibria, if I try to steer to a fully mixed equilibrium, I can't dissuade the pure equilibrium without giving some payment. But the problem is because the equilibrium that I want to steer to is fully mixed, any payment that I give will necessarily appear in the equilibrium. So this is essentially some intuition showing that I can't do much better than I have to do something more than the model that I showed previously. Which we solve by giving advice. Okay. So if I give advice, well, I can do actually a lot better than any mixed Nash equilibrium, right? I can steer to any base correlated equilibrium. I can steer to basically any equilibrium of this sort of like augmented game where the mediator is observing play and is capable of giving advice and payments, right? So given any base correlated equilibrium, I can convert it to this augmented game in which obeying all the recommendations is pure Nash. 4 minutes. Okay, I will be short of 4 minutes, I think. I just have one more thing to say, which is we have some experiments. And okay, so we tested on a bunch of games, and essentially what you should be looking for is that for the sake of our testing, we said, okay, for the first 10 iterations, the agent is going to be allowed to learn without payments. So without payments, the agents will basically just run no regret learning algorithms. There's no real guarantees of convergence, and indeed, in most of the games, like for example on this left game here, their social welfare is this green line here, which stays rather low and messy. On the 10th iteration, we start instituting these payments, and immediately the social welfare jumps, and this dotted line here is the social welfare of the best equilibrium, and we're able to steer the agents indeed toward that. And the amount of payment will decay with time. And this is the same for the other games. And indeed, for this game, it's actually quite quick. It only took like one iteration essentially to steer. Okay. And to conclude, I just want to state some interesting further questions here. So we studied a quite specific instantiation of this problem, which is pure Nash equilibrium, and although we generalized like basically given the equilibrium and given a mediator who knows everything about the game, and we have a lot of assumptions of this form. So an interesting question for future research is can we relax any of these? So for example, can we steer while simultaneously learning the equilibrium? Well, we explore this in the full paper, but the picture is not clear. Especially in extensive form with trajectory feedback, it's not clear whether this is possible, or even in some sense, it's not even clear how to best define this problem. Are the rates that we get optimal? Well, we don't know. It's possible that we could do better. We have no lower bounds matching. Is it possible to do better with specific learning algorithms? It's quite likely that if I make stronger assumptions on the behavior of the agent, so for example, if I assume that they're mean based, or if I assume that they're using a very specific algorithm like multiplicative weights or gradient descent, we should be able to do better than the bounds that we get. And it's possible that we might even be able to get away with this like order 1 payment, which for general no regret learners, as I've said, we can't do. And the final interesting question that I have here is, if the mediator has incomplete information about what the players are doing, can we still steer? Well, I mean, we have so the algorithm that we have right now sort of assumes that the mediator observes exactly, the state of the game and at every time step, and knows exactly the terminal node that's been reached by the players. What if the mediator doesn't do this? Can we still do anything? I don't know. Interesting question for the future. And yeah, that's all I have.